Okay, so proof by induction is one of the hardest proofs, I'd say, to get used to. It does have a very sort of formulaic structure to it, so a lot of people tend to like it. But induction, as a lot of the harder questions come from induction, so I'm going to do a couple of induction ones. Now, the steps required for induction are the following. You first start with what's known as the base case. So this is the lowest possible number. So for instance, if it was for all numbers greater than or equal to 3, you would start at 3. But if it was greater than 3, you'd start at 4. So you start at the lowest possible case that is presumed to work. And that's what's called the base case. The next one is called the induction hypothesis. So with this, actually I should know here that this is, say, for n equal to 1. The induction hypothesis says that, okay, if it works for this, then it works for all numbers that fit this category. So we'll just call it all valid numbers. So this is for n equal to k, where k is greater than or equal to the base case, which I'll just label this as nb. So this is 4, for example, you would say n equal to k, where k is bigger than 4. You could also say n equals k plus 4, where k is bigger than 0, but I tend to have it as just k, where k is bigger than the base case, because it just makes the algebra easier. And I apologize for my voice breaking there. Now the last one is called the proof case. This is where you say, okay, it's true for some number greater than the base case. Let's see what happens if we do the number right after it. So this is just a case for every next number. How you do this, you set the required variable equal to k plus 1, where the k plus 1 is the number after k bigger than the base case, which we assume works. So the steps, when I describe them, it just sounds a bit odd. So I'm going to go through a couple of examples, starting with this one. Prove that the sum of the first n squared numbers is the sum from n equals 1 to n of n squared is n times n plus 1 times 2n plus 1 over 6. Okay, so we're going to start stage 1. The base case here is n equal to 1. So what we're expecting is, we know that the sum from n equals 1 to 1 of just 1 squared is 1. So we're going to have 1 times 1 plus 1 times 2 lots of 1 plus 1 over 6, which is 3 times 2, which is 6. 6 over 6 is 1. And we say, therefore, true for n equal to 1. And I tend to like adding a tick. Next up, this is the assumptive case, or the induction hypothesis. It doesn't matter. I tend to switch between the two. It's formally called the induction hypothesis, but I call it the assumption case. What we say is that we assume 1 squared plus 2 squared plus 3 squared plus da 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 plus k squared is equal to, when we replace up to k here, we'll have k times k plus 1 times 2k plus 1 all over 6. We're going to assume that that's true. Now for the third one, we change the k now to a k plus 1. So what we're going to have is 1 squared plus 2 squared plus 3 squared plus da 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 plus k squared plus the next number k plus 1 squared. Now, the way you write this is a bit, well, it tends to trigger some people. But I'm going to write this as like a question mark. So we're going to have k plus 1. Then we're going to have k plus 1 plus 1. And then 2 times k plus 1 plus 1 all over 6. So that's how we're going to work it. We want all the k's, so the initial k's, to become k plus 1s. So what we're going to do is we're going to take this 1 squared plus 2 squared plus da 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 up to k squared, and we're going to label that as 2. So we're going to take it from the assumption case, and we're now going to have k times k plus 1 times 2k plus 1 over 6 plus, now k squared, k plus 1 squared I'm going to write is just k squared plus 2k plus 1. Now we want this all over 6. So I'm going to actually expand this out first. So we'll have a k squared plus k multiplying with 2k plus 1. And then we're going to have a 6k squared plus 12k plus 6 on the top over 6. Now expand these out, we get 2k cubed plus k squared plus 2k squared, 2k plus k squared, and then 2k squared plus k. It does take a lot of concentration with these, plus 6k squared plus 12k plus 6 over 6. Okay, so what we're aiming at is for this. So what you can say is if we bring this down, this is actually simplifies to k plus 1 times k plus 2, and then we get 2k plus 3 chilling out here. Now if we expand this, we'll get a k squared plus 3k plus 2 chilling in here, and a 2k plus 3, not 13. So k squared multiplying, we get a 2k cubed plus 3k squared plus 6k squared plus 9k plus 4k plus 6. Now if we simplify this, we get a 2k cubed plus 9k squared plus 13k plus 6. So that's what we're looking for. We have 2k cubed. Now we have a 6k squared, a 2k squared, and a k squared. So 6, 8, 9. So it's going to be plus 9k squared. Then we have a k plus 12k, which gives it 13k. And then the plus 6 left on its own. So plus 6 over 6. And then because you've quoted this, I'm just going to link the two. We can go back all the steps and have this as k plus 1, and then k plus 1 plus 1, and then 2 times k plus 1 plus 1 all over 6, which proves the statement. Now, how you write a conclusion angers a lot of people, but I'm going to go through it. So therefore, true for n equals 1, and by assuming true for n equals k, where k is greater than or equals 0, I should have said that actually. Assume n equals k for k greater than 0 proves n equals k plus 1. Therefore, the statement is true for all n greater than 1. And that's the proof.